Good morning and welcome to our presentation on thermal properties of matter. We will be discussing and exploring different kinds of thermometers, as well as the materials used to measure temperature accurately. We will be looking at the advantages and disadvantages of various thermometric substances and how they can be used in different contexts. Let's get started. Thermometers are instruments used to measure temperature. There are various types of thermometers, all of which employ materials that react to temperature changes. These materials include liquids, metals and gas. The most common type of thermometer is the liquid in glass thermometer, which uses either mercury or alcohol as the temperature-sensitive liquid. Other types of thermometers are bimetallic strip thermometers using metals with different thermal expansion coefficients, gas thermometers, and thermistors using semiconductor materials. Thermometers are necessary for accurately measuring temperatures and aiding in diagnosing and treating various medical issues. Thermometers are an important tool for measuring temperature variations in a variety of settings. They come in many different types, and the type used will often depend on the application. Resistance thermometers, gas thermometers, liquid thermometers, radiation thermometers, thermoelectric thermometers and vapor pressure thermometers are some of the types of thermometers used in the field. Each type has its own unique properties that allow it to measure temperature more accurately and efficiently depending on the task. Thermal properties of matter are essential to comprehending the characteristics and behavior of physical materials. This slide looked at two thermal properties of thermometers, cylinder contour and alcohol content, and how they influence the thermometer's sensitivity. Cylindrical thermometers, with greater surface area, are more sensitive to temperature differences compared to spherical thermometers. Moreover, alcohol thermometers are more sensitive than mercury thermometers as alcohol is capable of increasing in size more extensively. Mercury is widely utilized in thermometers due to a variety of advantages. Its specific heat capacity and vapor pressure are low, making it a perfect temperature reading material. Furthermore, its coefficient of real expansion is greater than that of most other substances, which makes it a more feasible choice. Additionally, it is opaque and emits a silvery glow, and does not wet the glass surface. Gases are often used in thermometers because of their unique properties. They have the same temperature coefficient, which means that a small change in temperature leads to a rapid expansion. Additionally, this temperature measurement process is not hindered by any impurities in the gas sample, making it a very precise way to measure temperature. Nitrogen and helium are two thermometric substances that provide an efficient and reliable method to measure temperature over a wide range. Nitrogen is capable of measuring temperatures up to 1500 degrees Celsius, while helium can measure temperatures below -200 degrees Celsius. Mercury is a remarkable element due to its unusually low melting point and high boiling point, making it suitable for thermometers. Moreover, its high heat capacity and low specific heat make it an ideal choice for measuring slight alterations in temperature, thus it is widely used for temperature measurement. Solids expand when the thermal energy of their particles increases, resulting in them vibrating more strongly and becoming further apart. This consequently increases the volume of the solid. This property of solids is employed for a variety of applications such as engineering bridge, sidewalks, and roads since they must include provisions to address variances in temperature and volume. Solids expand when heated due to the increase in interatomic distance between the atoms. Isotropic solids expand uniformly in all directions, allowing them to retain their shape and size when exposed to temperature changes, making them useful in many applications. Anisotropic materials are materials that have different properties depending on the direction in which the material is measured. Examples of anisotropic materials include Christiana, a form of Ca-3, and galena, a lead ore. Thermal expansion of solids is different for isotropic and anisotropic solids. Isotropic solids like metals and amorphous solids such as glass experience the same thermal expansion in all directions. On the other hand, anisotropic solids experience different thermal expansion depending on the direction in which they are measured. Substances can contract when heated. Examples include cast iron, silver iodine, silica glass, rubber, leather, ice, lead, and many more. The thermal energy in the material causes the molecules to move closer to one another, resulting in a size decrease. How much contraction occurs and how it is measured can depend on the material. Matter's thermal properties concern the kinetic energy and potential energy of molecules in a substance. On heating a body, these energies augment. The translatory kinetic energy of molecules rises, causing a temperature rise. In solids, the boost in kinetic energy is both rotational and vibrational. Grasping how thermal properties of matter influence its behavior is central to numerous scientific and engineering purposes. Potential energy of a solid is calculated by the attraction force between its atoms. At a particular distance of separation, the strength of attraction is the most powerful, resulting in a minimum potential energy and thus a state of stability. This is accomplished by setting up the atoms in a typical arrangement called a lattice. As the molecules get nearer, they gain potential energy because of the intermolecular forces in between them. After a balance is set up, the atoms reach a definite state of vibration at the specific distance of separation, allowing the solid to have a determined size. As can be seen in this graph, the relationship between interatomic distance and potential energy is clearly displayed as a curve. As the distance between atoms increases, so too does the potential energy between them. The potential energy reaches its maximum when the interatomic distance is at its maximum. When the distance between atoms decreases, the potential energy follows its own curve to reach its minimum. This illustrates how the structure of matter can be understood in terms of thermal properties. Answer. The correct answer to this question is D, as both rubber and silver iodine are solids which contract when heated. Knowing the thermal properties of matter is beneficial in being able to better interact with them. When talking about thermal properties of matter, anisotropic solids are those that have different properties in different directions. Examples of anisotropic solids include crystalline Ca-3 and silver iodine. Both A and B are true. Thermal expansion is a phenomenon that occurs when an object is subjected to a change in temperature, typically leading to an expansion or contraction of the object's size. The ratio of the change in length of the object to the change in temperature is called the coefficient of linear expansion. Each material has its own coefficient of linear expansion, based on how much the material expands per degree of temperature change. This coefficient is important for engineering and other applications, as it helps us to identify how various materials will respond to temperature changes. The expansion or contraction of materials in response to heat is due to the way the molecules in the material respond to the heat. The coefficient of linear expansion describes the increase in length of a solid when heated. The ratio of the increase in length to the original length is known as the coefficient of linear expansion. In this example, two rods were heated for equal amounts, and it is evident that the rod heated from 100 C to 1000 C had a greater increase in length than the one heated from 1000 C to 2000 C. The coefficient of linear expansion, also known as the coefficient of thermal expansion, is a physical property of matter with an SI unit of K1, or the CGS unit of 0C-1. It has a dimensional formula of M0L0T0K1, and is given by the equation equals L2L1L1, T2T1. This equation represents the change in length of a substance for every degree of temperature change, whether increase or decrease. By being aware of the coefficient of linear expansion, engineers and scientists can predict the behavior of different materials when temperatures change. Thermal properties of matter are an essential part of science. The coefficient of linear expansion of a solid varies based on the material and temperature range, being unique to each material. To illustrate, iron has a coefficient of 12 by 10 to 6, 0C, whereas copper and brass have coefficients of 17x10⁻6 over 0C and 18x10⁻6 over 0C respectively. Additionally, the linear expansion of a solid is determined by three factors: the original length, the kind of material, and the temperature change. The thermal properties of matter are of great significance. Analyzing the link between length change and temperature change reveals that the margin of increase or decrease in length is related to the temperature. The equation displayed on this slide states that the variation in length is equal to the coefficient of linear expansion times the initial length multiplied by the gap between final and initial temperature. In simpler terms, when temperature rises, the length of an object will increase, and when temperature drops it will decrease. The slide is asking about the substance with the smallest coefficient of linear expansion, and the answer is Invar, an alloy of iron and nickel. Invar is highly valued due to its unique property of an extremely low coefficient of linear expansion. It is widely used in industries for components that require extreme accuracy and performance. When pouring boiling water into a thick glass tumbler, the glass will often suffer from cracks caused by unequal expansions. This is due to the thermal expansion coefficient of glass, which is greater than 0, meaning the glass will expand more than the boiling water. The coefficient of areal expansion is an important thermal property of matter. It is the measure of the change of an object's area when exposed to a change in temperature. Measuring this property accurately is necessary to predict the behavior of materials in varying environments. Knowledge of the coefficient of areal expansion is key to success in engineering. Heat plays a significant role when working with matter. The coefficient of areal or superficial expansion of a solid can be expressed as the rise in area of a solid per unit original area for every unit of temperature increase. To illustrate, if we measure the area of a material at 10 degrees Celsius and afterward measure the area of the same material at 20 degrees Celsius, the difference will be the coefficient of areal or superficial expansion. This measurement is critical for grasping how materials respond to changing temperatures. We are discussing the thermal properties of matter, focusing on the calculation of the coefficient of areal expansion when looking at a given solid with two different temperatures. This coefficient is expressed as AK-1 in SI units, or a 0C-1 in CGS units. Its dimensional formula is M0L0T0K1, indicating that the measurement is independent of mass, length, and time. Examining the difference in temperatures allows us to calculate the fractional change in area. The coefficient of thermal expansion, beta, when multiplied with the difference in temperatures, T2 T1, yields the percentage of fractional change in area. This percentage can then be used to determine the final area, A2, by multiplying A1 with 1 plus beta, T2 T1. The thermal properties of matter can vary based on its structure. For anisotropic solids, the coefficient of areal expansion is determined by taking into account the linear expansion coefficients in the different directions. With isotropic solids, The areal expansion coefficient can be determined by calculating the average of the linear expansion coefficients. Which of these is an example of expansion of solids? The answers are A. Linear, B. Areal, C. Cubical, and D. Volumetric. Expansion of solids is the increase in area of a solid per unit original area per unit rise in temperature. There are four kinds of expansion: linear, areal, cubical, and volumetric. The SI unit of thermal conductivity, known as beta, is expressed as K1, which stands for Kelvin per meter. It is used to measure the rate of transfer of heat through a material or object. Thermal conductivity is an essential property of matter that enables the calculation of heat flow through it, thus allowing us to understand the effectiveness of materials, objects, or systems in transferring heat. Answer: C is the correct answer to this question. Areal expansion is a physical property of materials that measures the increase in its surface area when it is subjected to a thermal change, with the dimensional formula being M1L1T0K. We are discussing the thermal properties of matter, focusing on the coefficient of cubical expansion. When heat is added to a substance, it expands, and the coefficient of cubical expansion measures the relative change in volume of the material. Knowing the coefficient of cubical expansion can help determine the temperature range and limitations of a material's use, so it is important to be aware of the thermal properties of matter when discussing it. The coefficient of cubical expansion measures how much an object's volume will change if its temperature changes. This is important to consider when taking into account the effects of heat upon an object. Knowing the coefficient can help engineers design safely and effectively for thermal changes. Thermal conductivity, denoted by gamma, is a significant physical property of matter that enables us to measure how quickly heat is transferred through an object. It is expressed in kelvins per second or in centigrades per second, depending on the CGS unit used. We can calculate the final volume and temperature of an object by using its initial volume and temperature with gamma. Its dimensional formula is M0L0T0K1. Knowing this property helps us to better comprehend the behavior of matter in different settings. Examining the thermal properties of matter, we observe that it can be either isotropic or anisotropic. To measure these properties, we can use the coefficient of linear expansion and the coefficient of cubical expansion. For anisotropic solids, the coefficient of linear expansion must be measured in each direction, and the coefficient of cubical expansion can be calculated from these values. For isotropic solids, the coefficient of cubical expansion is equivalent to 3 times the coefficient of linear expansion. Further, the change in area can be measured to calculate the percentage change in volume with the coefficient of cubical expansion. Thermal properties of matter can be defined by 3 primary quantities: alpha, beta, and gamma. Alpha is independent of units of length, beta is 2 times of alpha, and gamma is 3 times of alpha. Additionally, alpha plus beta is equal to gamma, and the ratio of alpha to beta to gamma is 1 to 2 to 3. Put simply, thermal properties of matter can be represented by the combination of these 3 values. The slide looks into how the density of a substance alters with temperature. With an increase in volume of the solid as temperature increases, its mass stays fixed, which leads to the decrease in density. An equation on the slide clarifies the link between the volume, mass, and density of a solid at distinct temperatures, as well as the coefficient of volume expansion for the solid. The equation is beneficial in understanding the way density changes when the solid is heated. answer. Gamma is measured in mass, length, and temperature, with its dimensional formula M1L1T0K. Thermal properties of matter refer to how different substances react to changes in temperature. Thermal properties of matter is an interesting phenomenon. Heat affects the volume of solid materials in that it increases the volume while the mass stays the same. This means the density of the material decreases. The correct answer to the question is C, decreases. Thank you for your attention.